What if I told you that some of the most important things in engineering, from keeping airplanes stable to making Netflix recommendations to helping robots understand the world, all depend on one surprisingly simple idea: organize numbers, then let them work together. That idea is linear algebra. In this video, we are going to break down the 5 biggest ways linear algebra powers engineering, not just as abstract math, but as a practical tool engineers use every day. A lot of people meet linear algebra as matrices, vectors, and equations on a whiteboard, and that can make it feel disconnected from reality. But in engineering, linear algebra is basically a language for describing systems with many moving parts. Whenever something depends on multiple inputs and outputs, linear algebra is usually hiding underneath. First, linear algebra helps engineers model systems. A vector can represent almost anything with multiple dimensions: position, velocity, force, color, sensor readings, you name it. A matrix can represent how one system transforms those values. This is useful because real engineering problems are rarely about one number at a time, they are about interactions. For example, in structural engineering, a building does not just take force. Different beams, joints, and supports all influence each other. Linear algebra lets engineers turn that complexity into equations they can solve. That means instead of guessing how a structure behaves, engineers can compute it. Second, it is one of the fastest ways to solve large systems of equations. If you have 2 equations and 2 unknowns, you can solve them by hand. But real engineering problems can involve thousands, even millions of unknowns. That happens in things like fluid simulation, electrical circuits, and heat transfer. Linear algebra turns all of that into matrix form, and then computers can solve it efficiently. A concrete example, in circuit analysis. Each node in a circuit obeys laws like Kirchhoff's laws. Those relationships become a big matrix equation. Solve the matrix and you know the voltage and current everywhere in the system. That is not just neat, it is how engineers design and test systems before building them. Third, linear algebra makes movement and rotation possible in computers and machines. If you have ever seen a 3D video game, a robot arm, or a drone navigating space, linear algebra is doing a lot of the heavy lifting. Matrices can rotate, scale, and translate objects in 2D and 3D space. That is useful because engineers need exact control over position and orientation. For example, in robotics, a robot arm needs to move from one point to another without colliding with anything. Linear algebra helps calculate each joint's position so the arm moves smoothly and accurately. In computer graphics, the same math helps render realistic scenes, camera angles, and animations. Fourth, it powers signal processing. Signals are everywhere: audio, Wi-Fi, radar, medical scans, vibration sensors, and those signals are often noisy. Linear algebra helps isolate the important information from the clutter. For instance, engineers use matrix-based methods to compress images, filter noise from sensor data, and analyze patterns in communication signals. A practical example is medical imaging like MRI. The machine collects raw data, and linear algebra helps reconstruct that data into an image doctors can actually interpret. So in a way, linear algebra helps convert invisible patterns into usable information. Fifth, it is the backbone of modern machine learning and optimization. If engineering is about building better systems, optimization is about finding the best version of those systems. Linear algebra helps computers handle huge datasets, compare features, and adjust model parameters. Vectors represent data, matrices transform it, and algorithms use that structure to learn patterns. That is how systems can predict failures in machines, detect defects in manufacturing, or improve control systems in real time. For example, in predictive maintenance, sensor data from engines or turbines can be analyzed to spot signs of wear before something breaks. That saves money, time, and sometimes lives. So the big takeaway is this: linear algebra is useful because it turns complexity into structure. It helps engineers model systems, solve equations, control motion, process signals, and build intelligent tools. It is not just math for math's sake. It is one of the main reasons modern engineering can be precise, scalable, and computationally powerful. The 5 biggest ways linear algebra powers engineering is just one small part of linear algebra. If you are interested, our full free linear algebra course is linked in the description.